Okay, so remember last class we talked about derivatives of integrals and how the fundamental theorem of calculus applies. Okay, so I'm going to write the note at the top of my page just as a reminder that when we're taking the derivative of sine, we get cosine. Derivative of cosine, we get negative sine. Derivative of negative sine, we get negative cosine. So going down this list, I would be taking a derivative. That means that going backwards on the list, using our fundamental theorem, that we would go backwards to integrate. We also need to know that the derivative of tangent is secant squared. So going down, we take the derivative. And going back up is for integration. The derivative of secant, down for derivative, is secant tangent. Up for integral means the antiderivative of secant tangent would be secant. Derivative of cotangent is negative cosecant squared. So the integral would go in the backwards direction. And lastly, if we want to take a derivative of cosecant, we get negative cosecant cotangent, so integrating to go backwards. Okay. So we're still allowed to hold any constant that was normally inside as long as it is a product. So the product of a constant just factors out. And so if we go backwards from sine according to our chart, remember sine and cosine are the only ones that work kind of in a circular pattern. So the going backwards from sine actually gets us to the bottom of the list, and we get negative cosine plus a constant. So we have negative 4 cosine of x plus c. Same idea, we can hold the constant for number 2, so I have a negative 2/3 that I can factor out. So we're just anti-deriving cosine of x. So negative 2/3. Going backwards from cosine on the list is a positive sine of x, and then plus c. Okay, secant squared is one of the ones that we have to memorize. Very frequently we try to think of secant squared as secant theta being squared as a U-substitution issue, and it really is not a U-substitution issue. It's one of the ones that we have to know and recognize and memorize right away. So going backwards from secant squared, we get tangent plus c. With that same regard, again, we really need to be so comfortable and so familiar with our derivative rules that we know going backwards quickly what they are, that 5 over cosine squared should really be rewritten as 5 secant squared. We can hold the 5, and going backwards from secant squared is tangent x. And then the entire antiderivative has a plus c. So you wouldn't see these remaining with the parentheses any longer on your answer choices. Remember, adding and subtracting are normal. We don't have any special rules for those. So going backwards, we hold the 10. Antiderive x to the 4th is x to the 5 over 5. Hold the negative 2. Going backwards from secant squared is tangent plus c. So we have 2x to the 5th minus 2 tangent x plus c. Remember, using your fundamental theorem, that if I want to check my answer, an antiderivative answer of this means that the original function was the derivative. So if this is y, then what's inside was my original y prime. So if you want to know if you've done your antiderivative correctly, you can double check by taking the derivative of the y function that you found. Going backwards from 4 cosine x minus 9 sine x, I hold the 4. Backwards from cosine is positive sine. Now it depends on the person. Some people like to hold the negative 9 and go backwards from sine. Others like to think of it as a 9 and a negative sine. Going backwards from negative sine is positive cosine, and then plus c. So again, if you want to check your answer, if you determine that this is your y function, then you could take the derivative and should get the y prime to match up to your original equation. Okay, now there are some instances where our trig identities really come into play. So if I have sine and sine squared together, I really want to look at how I could substitute this out to get a cosine version of that. So remember that we have sine squared plus cosine squared equals 1. We talked about that last class. So that would mean that 1 minus sine squared would equal cosine squared. So we have sine of x, the x on top, and cosine squared on bottom. That actually simplifies out to give me sine of x over cosine of x. And then we can think about it as dx over cosine x if we want, so that we have a cosine squared on bottom and a sine x and a dx on top. That means that I'm anti-deriving tangent of x, and 1 over cosine is secant of x dx. And again, we have to know instantly what these work out to be so that we've memorized so well that we recognize when we have things that are part of just normal derivatives and don't need a special rule. So here, if I were to go backwards or forwards from secant tangent, we just get secant. And one more time, if we want to know if this is correct, if this is my y function, fundamental theorem of calculus tells me that this was my y prime. So I'll know if I've done the right thing. Okay, so don't panic if the letters aren't always called x. That's perfectly acceptable as long as whatever letter you're using matches what you have on the outside. So what you're taking the derivative or the integral with respect to. In this case, we would just treat this like x. Okay, going backwards from negative cosecant squared. Okay, so I'm going to hold the 2, and negative cosecant squared is the derivative of positive cotangent. So if I were to double check my answer, I would get 3 over 3 theta squared plus 2, and the derivative of tangent would be negative cosecant squared, and the derivative of a constant would be 0. So I do, in fact, if this is my y function, this would be my y prime function would match. So I know I've done the right thing. Okay, so for our next function, going backwards from secant squared, we have to know so well that that is just tangent. Going backwards from cosine is just sine. Going backwards from 1 is a plus t, and then plus c is always there for an indefinite integral. Going backwards from 1 is x. I have a 6 that I'm going to hold, and then going backwards from negative cosine is negative sine plus c. Even though we've started doing trig, doesn't mean that our polynomial rules have gone away. I'm still going to rewrite that as x to the negative 2. I still have negative sine x dx. X to the negative 2 still becomes x to the negative 1 over negative 1. Negative sine goes backwards to be positive cosine and plus c. And we would never see a multiple choice left this way. So I could rewrite and have my function. So for this one, again, I would factor out the constant and just be left with 3/5 cosine x dx. So the 3/5 stays. Going backwards on cosine, I get sine of x. And the entire integral has 1 plus c mark. Okay, so sine squared x plus cosine squared x would be a very hard antiderivative to do, although we could do it. It would eventually cancel off because sine squared plus cosine squared is just 1. So going backwards from 1 is x plus c. Okay, so remember the only ones that we really need you to know for AB are sine squared x plus cosine squared x equals 1. Tan squared x plus 1 equals secant squared x. 1 plus cotangent squared x equals cosecant squared x. And the other big one that we use frequently is the sine double angle. So sine of 2x is 2 sine x cosine x. Okay. Now we have solved differential equations already with polynomials, where we work our way backwards and solve for a plus c and then possibly a plus c2 or a plus d, depending upon what you want to call it. So we have to remember that f of x, using the fundamental theorem of calculus, is the antiderivative of f double prime of x. So that's going to be the antiderivative of cosine of x dx. And going backwards from cosine, we get positive sine plus a constant. Okay. So again, going backwards from f double prime, let me make sure those are legible for you. Going backwards from f double prime gives me f prime. So now I'm going to use the initial condition that says f prime pi, which would now be sine of pi plus c, has to equal 2. So that means that 0 plus c has to equal 2. So c equals 2. That means that I have solved just for f prime of x. I only know that f prime of x is sine of x plus 2. I now have to continue going backwards with the fundamental theorem that says f of x is the antiderivative of f prime of x dx. So that's going to be the antiderivative of sine x plus 2 dx. Going backwards from sine, I get negative cosine of x. Going backwards from 2, I get plus 2x. And then I have a different letter, so I'm going to use d in my case, but you could use c2 or c1 or something that indicated it was different. And so that is going to be my f of x. Now I'm going to use my other initial condition that says that f of pi, which is negative cosine pi, plus 2 pi plus d, has to equal negative 1. So negative cosine pi is negative 1, plus 2 pi plus d has to equal negative 1. So that means that d is actually going to be negative 2 plus 2 pi, sorry, minus 2 pi. That means that my f of x function, which is the solution to this differential equation problem, is negative cosine of x plus 2x minus 2 minus 2 pi, which replaces the d. Okay, so this is a similar question to the one we just did, only this time they're giving us a multiple choice. So if the second derivative is given by this, notice the wording says which could be f of x. The reason they're saying could be is because unlike the last problem, they didn't give us any of the initial conditions, so I cannot solve the plus c and I cannot solve the plus d, but I can still do the setup for getting the backwards and know which one of these is a possible f of x. So remember, f prime of x goes backwards from f double prime of x dx, which is anti-deriving 2x minus cosine of x dx. That means that I get 2x squared over 2, so the 2's cancel. But going backwards from negative cosine gives me negative sine plus c. If you're having trouble remembering those, it's always okay to put them at the top of your page. Sine, cosine, negative cosine. Remember, down for derivative. and then backwards for integration. Okay, now f of x is going backwards from f prime of x, which means we'd have to antiderive what we just found. But we can't just throw the plus c away because we didn't know the value. It means it's still there. We simply don't know what the value of the constant is. So going backwards from that is going to give me x cubed over 3. Negative sign ends up as positive cosine because we're going backwards. An unknown constant goes backwards to be that constant times x. And then we have a different unknown constant. So remember, if you're wanting to check to see if you've done these correctly, I'll actually call this one f of x. And if this is my f of x, it should have the f prime that we found as its derivative. So make sure that you've done that right. So now I need the one that has a positive x cubed over 3 and a positive cosine, and another constant x, and then another d. So we know right away that it can only be answer A. Okay, so now we're going to start in with some definite integrals. So the only difference is we won't have the plus c. And we're going to have to do the fundamental theorem that requires us to substitute top minus bottom. So going backwards from cosine, and again, if you're allowed to write those every time if you want to, sine, cosine, negative cosine, down for derivative, backwards for integration. Going backwards from cosine, I get sine of t. I don't need the plus c because we're doing the top minus bottom. And then we do substitute in the top minus the bottom. And it just so happens that the sine of 0 is 0. Not all trig functions are just 0, though. Be very cautious. So we end up with just sine of x. I can keep the 4 that's factored out. Going backwards from cosine, I get positive sine. And from negative pi over 4 to pi over 4. I'm going to hold that constant and just deal with the trig on the unit circle that I absolutely have to memorize by now. So I have sine of pi over 4 minus sine of negative pi over 4. Again, I'm going to hold the 4. And I get root 2 over 2 minus a negative root 2 over 2. So that actually makes these positive. And I get root 2 over 2, but I have 2 of them. So it cancels, really. So I end up with 4 root 2. Some people prefer to distribute through, and that's fine as well. But that would have given me 4 halves, or 2 root 2, plus another 2 root 2, which still would have given me 4 root 2 overall. Anti-deriving 2, remember we're going backwards. A very common mistake is for students to put 0 because you kind of mix up doing integration and derivatives. But going backwards, we have 2x. Backwards from sine is negative cosine from 0 to pi. So now on this type of question, you want to be cautious on your FRQs that you are allowed to substitute in top minus bottom, but have to be cautious that your parentheses are there. If you write something that's algebraically incorrect in a step, let's say I decide to leave off the parentheses altogether, and I were to write something like 2 pi minus cosine pi minus 2 times 0 minus cosine 0, that is actually an incorrect step in the middle of your answer. And as you go through, since you're not allowed to leave cosine, because that's not an algebra step, we're allowed to leave arithmetic and basic algebra like that undone. We're not allowed to leave trig undone. It's part of our pre-calc A part of the Calc AB. It would not even be okay if we left it that way and then went on to get the correct answer, because it just so happens we have a 0 there. Even if we did put a +1, which is the correct response, it has to be those parentheses for that step. So you really need this to have this process done. You can't have any steps written incorrectly. And it's very infrequent that people who write the intermediary steps incorrectly salvage it and manage to get the right answer in the final result. But even on an FRQ that you did not have to simplify, it would still be an intermediary step that's wrong. You would still lose the point. Going backwards from 4x, we have 4x squared over 2. Backwards from secant squared, remember we have to have memorized the tangent x. And from 0 to pi over 4. So I can simplify out. I have top 2 pi over 4 squared plus tangent pi over 4 minus the bottom, which is 0, plus tangent 0. So I have 2 pi squared over 16 plus the tangent of pi over 4, which is 1, minus, it just so happens that the tangent of 0 is 0. So I would have pi squared over 8 plus 1. Going backwards from cosine, remember is positive sign. From negative pi over 2 to pi over 2. So it's top minus bottom. So that's 1 minus a negative 1. So we get 2. Again, be very careful in this type of situation without your parentheses, or if you're not cautious with your arithmetic. I see a lot of students inadvertently write 0 for an answer like that. Backwards from 2x gives us x squared. Backwards from negative sign is positive cosine, 0 to pi. The top is pi squared plus cosine pi, minus the bottom, which is 0 squared plus cosine 0. Now again, this is one of those things I said to be cautious about with trigonometry. Unlike polynomials, plugging 0 in for the x doesn't make the whole thing go away. We have pi squared. Cosine pi is negative 1. And cosine 0 is not 0, it's 1. So we have pi squared minus 2. Okay, for the next one, going backwards, we keep the 3. And again, I almost forgot for you. If I wanted, I could put the sine, cosine, negative cosine at the top of my page. Down for derivatives. Up if we're going backwards for integration. So backwards from sine is negative cosine. Backwards from negative cosine is negative sine. And then plus c. Only, oops, we don't really need the plus c because we're doing a definite integral. From 0 to pi over 2. So top minus bottom, parentheses are necessary. Negative 3 cosine pi over 2 minus 2 sine pi over 2 minus, plugging in the bottom, parentheses, negative 3 cosine 0, negative 2 sine 0. So the cosine of pi over 2 cancels because that's 0. The sine of 0 is 0, so this piece cancels. So I have negative 2 sine pi over 2, which is 1, minus negative 3 cosine 0, which is 1. So being very cautious with my arithmetic, we get 1. So don't let the arithmetic be the reason you miss a relatively simple multiple choice question. All right, so going backwards from x is x squared over 2. Going backwards from negative secant squared is negative tangent. Then from 0 to pi over 4. So the top, pi over 4 squared over 2 minus tangent pi over 4 minus the bottom, which is 0 squared over 2 minus tangent 0. Now you have to be cautious with that fraction. Pi squared over 4 squared, which would be 16, divided by 2. Now you have to be very careful that when you divide by an answer, like dividing by 2, that you don't get the same thing as if you were multiplying by 2. Those should never be the same result. So if I have pi squared over 16 divided by 2, it should not end up being pi squared over 8. You're dividing this fraction by 2, which is the same thing as multiplying by the reciprocal, which actually makes it pi squared over 32. We have minus the tangent pi over 4, which is 1. And the nice part is that 0 becomes 0, and tangent of 0 is also 0. So we're just left with this answer, pi squared over 32 minus 1. Okay, now remember what we said about knowing your derivatives and integrals quickly so that you can get through them fast. Going backwards from secant tangent is secant theta from 0 to pi over 3. So secant pi over 3 minus secant 0. Kind of a reminder of your unit circle. Secant is 1 over cosine. Cosine is a half at the pi over 3 and 1 at the 0. So we're going to have 2 over 1 minus 1 over 1. So just 1. Okay, going backwards from sine, we get negative cosine. Remember, we're going backwards, and that's really hard to get used to, especially as quickly as we go through the pace of the course. So going backwards from sine is negative cosine. I'm going to hold that negative. The reason I'm doing that is because it makes it a lot easier for me to not make an arithmetic mistake. So that now when I substitute in, I just have cosine of x minus cosine of 0. And I don't have to worry about, was it positive? Did I need to take a double negative because it was already negative? So now if I look at this, I have a negative on the outside, cosine of x minus 1. So that makes negative cosine x and plus 1, or 1 minus cosine x. Okay, so now we also need to be able to use sub in order to do antiderivatives with trig as well. Remember that U-substitution is when the inside is not just plain x. So for example, on this first problem, we have sine of 2x, not plain x. I can't just ignore the 2 or throw it away. There would be a trig identity for that. Remember that sine of 2x is 2 sine cosine. So there's a product rule involved. Remember, we're not really going to undo the product rule. We've only undone chain rule. So let's do it that way. Our u is going to be 2x. That means the derivative of u with respect to x is 2. We cross multiply to get du equals 2 times dx. So 1/2 of du equals 1 dx. Now we're going to do our substitution. So we have the integral, we have sine, we're going to swap out our u, and we're going to swap out our dx, and the dx is really half of du. So we hold the half. Going backwards, the antiderivative of sine is negative cosine plus c. So we have negative 1/2 cosine. And since we don't have limits on here, we're going to have to take that x back because we are actually looking for the function that has the derivative of sine 2x. So since we don't have limits, we have to get back together with our x. Okay, now what's inside this time is that we have a 2x. Otherwise, if it weren't 2x, we have secant tangent, and we know that that goes backwards to be secant. So our u is going to be 2x again, which makes our du, just like the last problem, 2 dx, and 1/2 du. So we have 1/2 the integral of secant u tangent u du. So 1/2, going backwards from secant tangent is secant, plus c. So I have 1/2 secant of 2x plus c. So again, notice what's inside is what's composited inside of another function. And sine of x is actually holding on to that x squared. So my u is going to be x squared. Du is 2x. And I'm going to go ahead and kind of skip a step and multiply that dx up there. So that means that du over 2x is equal to 1 dx. Remember, I'm only allowed to substitute out the dx and the u. So I'm going to keep the x. It's going to be sine of u now. And dx is du over 2x. So fortunately, that x part cancels. And so I really just have a half. Going backwards in sign is negative cosine u plus c. So I have negative 1/2 cosine getting back together with our x because we don't have limits. We just keep taking the x back. Okay, so for the next part, what is composited inside is what's inside of the sign. So my u is x to the 1/2. My du is 1/2 x to the negative 1/2, and I'm going to go ahead and multiply that dx across. So this really reads as dx over 2 square root of x right now. So instead of being du over this time, because we're really cross-multiplying, we end up with 2 root x du goes in for dx. So this is what we're substituting for dx. So I'm only allowed to substitute out the u. So I have sine u. I have to leave the rest, and I can substitute out the dx. It's 2 root x du. I still, fortunately, get a cancellation for the root x part. So I have anti-deriving 2 sine of u du. Going backwards from sine is negative cosine. So I have negative 2 cosine getting back together with my x plus c. Okay, now, number 30 is an example of really one of the hardest types of U-subs for us to do because we get a little confused about what's technically inside. I'm going to rewrite this. And a lot of people want x squared to be our u, but really our u needs to be the thing that simplifies everything the most. So it's really going to be this sine of x squared that's all the way inside the cube. It's a little bit trickier. So now my u is the sine of x squared. My du requires the chain rule. Derivative of the outside is cosine times the derivative of the inside, which is 2x. And I'm really multiplying that dx over. So that means that du over 2x cosine x squared is equal to dx. But if we go back now to our integral, we have x u cubed cosine x squared, and when we change out that dx now, we have du over 2x cosine x squared. So that is going to allow us to cancel not only the x, but also the cosine x squared. So we're anti-deriving 1/2, because don't forget that little 2 we left behind, u cubed du, which is 1/2 u to the 4 over 4 plus c, which is 1/8 u to the 4th plus c. And since we don't have limits, we're going to take our x back and our x was sine of x squared. You would probably see this written as 1/8 sine to the 4th x squared plus c. Okay, for the next one, we have cosine root x. In this case, the root x is our u. So du is 1/2 x to the negative 1/2 dx. So 2 root x du equals dx. So I have the square root being replaced only for the u. Everything else has to stay the same. And my dx is 2 root x du. So for cancellation, we keep the 2. Going backwards from cosine is sine plus c. So it's 2 sine root x plus c. Okay, so similar to number 30, this one can be a little bit tricky because we have a cosine and then a sine squared. This could be done as a U-substitution, but it doesn't really have to be done as a U-substitution. I could rewrite this one as cosine theta over sine theta, 1 over sine theta, d theta, which is going backwards from cotangent, cosecant. And you might recall that cosecant cotangent is almost the derivative of cosecant. The derivative of cosecant is negative cosecant cotangent. So if I go backwards, I actually get the opposite of cosecant plus c. This function would have this as its derivative. That isn't the only option though. So for number 33, for example, that would be a similar situation. But I could choose to do this as a u-sub. So if my u were cosine of x, because that is inside the square, then du would be negative sine x dx. So du over negative sine x would equal dx. So that would mean that I have a negative sine x over u squared, and I would replace my dx here. So this would be du over negative sine x. And the negative sine x completely cancels. So I'm anti-deriving 1 over u squared du, which is anti-deriving u to the negative 2 du, which is u to the negative 1 over negative 1 plus c, negative 1 over u plus c, so negative 1 over the cosine of x plus c, which is equivalent to negative secant x plus c. So notice how the u-sub version of this one actually takes us a lot longer than if we were to simplify this out the way we did here. And we could have seen immediately that we had negative secant tangent. Okay, 34 has to be a u-substitution. My u is the inside part. Du is 4x cubed dx. So du over 4x cubed is dx. So in my problem, I have x cubed cosine u, and the dx is du over 4x cubed, and those cancel. So I have 1/4. Going backwards from cosine is positive sine plus c. So it's 1/4 sine of x to the 4th plus 2 plus c. Now, what happens when we do have limits? Remember when we have limits that we never, ever, ever get back together with our x. So in this problem, the inside part, what's inside of another function, is the 1 plus sine theta. That means du is cosine theta d theta. So du over cosine theta equals d theta. So substituting out, remember we're only allowed to substitute the u. We're allowed to substitute the derivative. Everything else has to stay and naturally cancel on its own, except we have to change our shoes. So if u is 1 plus sine theta, if I substitute pi over 2 in for theta, I get 1 plus 1, which is 2. If I substitute 0 into 1 plus sine theta, I get 1 plus 0, which is 1. The cosines happen to cancel, but remember that square root is on the bottom. So that means we're integrating 1 to 2, u to the negative half du. So as I go backwards, I get u to the positive half divided by a half, which is multiplying by the reciprocal, from 1 to 2. Remember, I hold the 2. So I'm just going to do the square root of 2 minus the square root of 1. So 2 square root of 2 minus 1, just d. For this next problem, my u is 2x. So du is 2 dx, and 1/2 du equals dx. So I have 1/2 sine of u du. If my u is 2x, then 2 times pi over 4 is pi over 2, and 2 times 0 is 0. I keep the half, go backwards from sine is negative cosine of u from 0 to pi over 2. And remember, we have limits, and when we have limits, we never, ever, ever get back together with our x. I'm going to factor out the negative and put it with the half so that I can just deal with cosine pi over 2 minus cosine 0 without having to consider sign changes and double negatives. So I have negative half. Cosine pi over 2 is 0, minus cosine 0 is 1. So I have negative half times negative 1, which is positive half. For 37, the u is the inside part, which is composited as cosine. Du is negative sine of x dx. So du over negative sine x equals dx. My integral then is sine x, square root of u, du over negative sine x. So I can cancel. So I'm integrating negative u to the 1/2 du, but I have to remember to change my shoes. So if I have 0 to pi over 2, plugging into cosine, cosine 0 is 1, cosine pi over 2 is 0. Notice that those are backwards. So I have to change them by flipping this over and switching the sign. So now it's positive. That makes us u to the 3/2 divided by 3/2 is the same as multiplying by 2/3 from 0 to 1. Remember that we always hold that constant and deal with it later. So I can usually do 1 to the 3/2 for top minus 0 to the 3/2 bottom, just holding the 2/3. So I have 2/3 times 1, which is 2/3. Okay, from 0 to pi over 6, going backwards, a little bit trickier. I'm going to do the 0 to pi over 6 and hold it, and do 1. Then I'm going to do 0 to pi over 6, and do sine x cosine x. This is a U-sub situation where you absolutely have to just know your derivative integral relationships hand in hand. So if I'm looking at sine and cosine, I know that if sine is my function, the derivative is perfectly cosine. Whereas if cosine were the function, the derivative would have to be negative sine. So I'm going to choose for myself to let u equal the sine of x. Because du would be exactly cosine of x, dx. So du over cosine of x is going to fix that for me perfectly. So just this integral on the right-hand side, the sine of 0 is 0. The sine of pi over 6 is a half. Sine is worth u. Keep the cosine, substitute out du over cosine x, and that cancels. So this just becomes u squared over 2 from 0 to a half. Keep the half. It's a half squared minus 0 squared. So I'm keeping this 2 factored out as a half. So it's a half squared minus 0 squared is 1/8. So that gives me that right-hand integral. This other one is just nice. Antiderivative of 1 is x from 0 to pi over 6. That's pi over 6 minus 0. So this carries all the way down. So my final answer is the pi over 6 plus the 1/8 that I had. Okay, similarly, going backwards, I'm going to hold the 1. So that's really just going to be x from 0 to pi over 12. So that's pi over 12 minus 0 and pi over 12. For the other part, I'm going to antiderive negative cosine of 2x dx. So my u is going to be 2x. Du is 2 dx. 1/2 du equals dx. So I have negative 1/2 cosine of u du. So that's negative 1/2, going backwards from negative cosine. So I can really think of this as a negative cosine becomes negative sine. Or going back from cosine is just sine, either way. But I had to change out my shoes. So 2 times 0 is 0. 2 times pi over 12 is pi over 6. So we're going from 0 to pi over 6 instead of 0 to pi over 12. So I have negative 1/2 sine pi over 6 minus sine 0. So that's negative 1/2 of 1/2, or negative 1/4. I can carry the other part down. I still have pi over 12, and now it's minus 1/4. For 40, my u is cosine of t. My du is negative sine of t dt. So du over negative sine t equals dt. So I have u cubed sine t dt over sine t to antiderive. And I have to change my shoes. Cosine of 0 is 1. Cosine of pi over 2 is 0. I still have the negative from the bottom here, but I also need to flip. So if I flip from 0 to 1, this now becomes positive u cubed, oops, typo there, du. So it's u to the 4th over 4 from 0 to 1, which is just 1/4 minus 0, so 1/4. For the next one, I have u equal to pi minus t squared. Remember, pi is a constant, so the derivative is just negative t, 2t dt. If I change these out, pi minus 0 is pi. Pi minus the square root of pi over 2 squared is pi minus pi over 2. And pi minus pi over 2 is pi over 2. I have t sine u. And now my du over negative 2t goes in for dt. So I have negative 1/2 from pi to pi over 2 sine of u du. Keep the negative half. Backwards from sine is negative cosine from pi to pi over 2. So that is positive half cosine pi over 2. So I'm putting the positive half together from here. Cosine pi over 2 is 0. Minus cosine pi is negative 1. So I get positive half as my answer. For 42, u is equal to tangent x. Du is equal to secant squared x dx. Changing out tangent of 0 is 0. Tangent of pi over 4 is 1. We have square root of u. Secant squared x dx is going to be du over secant squared x. So I have u to the 3 halves divided by 3 halves from 0 to 1, which makes this 2/3 times 1 minus 0, so just 2/3. For 43, my u is 1 minus cosine squared, which is a little bit sad. So we need to really change that out to be sine squared. Only problem is that could still simplify nicer inside the equation. So we're going to simplify it first. So I have 0 to pi over 3 cosine x, square root of sine squared x. So I have 0 to pi over 3 cosine x, sine x. So remember, I'm going to choose sine to be my u, because then the derivative of u is cosine x dx. So this part is exactly du. Sine of 0 is 0. Sine of pi over 3 is root 3 over 2. So those are really exactly du. So I'm just left with u du. So I have u squared over 2 from 0 to root 3 over 2. I'm going to hold the 1/2 to root 3 over 2 squared minus 0 squared. Hold the 1/2. That's 3 over 4. So I get 3 over 8. And finally, one last problem. If u is the square root of x, du is 1/2 x to the negative 1/2 dx. Du times 2 times root x is going to equal dx. So I have sine of u, square root of x on bottom, 2 root x du on top. So those cancel. Changing my shoes. I have to take the square root of each limit because that's my u. So the square root of pi squared is pi. Square root of pi squared over 4 is pi over 2. So I have 2 from here, remember, antiderivative of sine is negative cosine from pi over 2 to pi. Makes this negative 2 cosine pi minus cosine pi over 2. So negative 2, cosine pi is negative 1, cosine pi over 2 is 0. So the final answer is 2.